For millennia, humans perceived the universe as a vast stage where the drama of existence unfolded. Space was the unchanging backdrop, a three-dimensional grid against which objects moved. Time, an independent river, flowed at a constant rate, oblivious to the events it marked. From the earliest stargazers to the scientific revolution, space and time were considered separate entities, fundamental and absolute. Ancient astronomers meticulously charted the heavens, mapping the positions of stars and planets against the celestial sphere. Time was measured by the cycles of nature, the rising and setting of the sun, the waxing and waning of the moon, the changing seasons. Isaac Newton, the father of classical physics, formalized this separation, forever changing our understanding of the cosmos. His laws of motion and gravity relied on the fundamental separation of space and time, a paradigm that would stand for centuries. Yet the universe held deeper mysteries, waiting to be unveiled by a mind bold enough to challenge the very fabric of reality. Isaac Newton codified the classical view of space and time with mathematical precision. His laws of motion and universal gravitation painted a picture of a clockwork universe. Space was an infinite, unchanging stage, a rigid grid against which all motion could be measured. Time flowed uniformly throughout the universe. Imagine a solitary object moving through the vast emptiness of space. We could define its position with absolute certainty, referencing the unchanging grid of space. This framework provided a powerful tool for understanding the motion of planets and pendulums. However, cracks began to appear in this seemingly perfect edifice. Experiments with light hinted at a deeper reality, where space and time were intertwined. In the early 20th century, a young Albert Einstein, working as a patent clerk in Bern, Switzerland, dared to question the very foundations of physics. Dissatisfied with the limitations of Newtonian mechanics, particularly its inability to reconcile with the emerging understanding of light, Einstein embarked on a journey that would revolutionize our understanding of the universe.
Einstein's breakthrough came with the realization that space and time were not independent entities but rather intertwined aspects of a single, unified fabric, space-time. Imagine a trampoline as a two-dimensional representation of this fabric. A bowling ball placed at the center will create a dip, distorting the fabric around it. This, Einstein proposed, is akin to how massive objects warp the fabric of space-time. Time, once considered absolute and universal, was now relative, its passage dependent on the observer's motion and the gravitational field they experienced. The universe, as envisioned by Einstein, was no longer a static stage, but a dynamic and ever-changing landscape.
Einstein's general theory of relativity, published in 1915, provided a new and profound understanding of gravity. No longer a mysterious force acting at a distance, gravity, according to Einstein, is a manifestation of the curvature of space-time itself. Imagine a marble rolling across the trampoline distorted by the bowling ball. The marble's path will curve as it moves through the warped region, seemingly attracted by the bowling ball. This is analogous to how objects move under the influence of gravity. Massive objects, like stars and planets, create depressions in the fabric of space-time. Smaller objects, caught in these gravitational wells, move along curved paths, seemingly drawn towards the more massive object. This prediction was dramatically confirmed during a solar eclipse in 1919, catapulting Einstein to international fame and solidifying his theory as a cornerstone of modern physics. One of the most mind-bending consequences of Einstein's theories is the relativity of time. Time, once considered absolute, is now understood to be relative, dependent on motion and gravity. This phenomenon, known as time dilation, has profound implications for our understanding of the universe. Imagine two identical clocks, one stationary and one traveling at high speed. The moving clock ticks slower than the stationary one. This difference becomes significant as objects approach the speed of light. Time is a fluid aspect of the cosmos, influenced by motion and gravity. Einstein's theories of relativity revolutionized our understanding of space, time, and gravity, ushering in a new era of cosmological exploration. However, despite their explanatory power, these theories do not provide a complete picture of the universe. The quest to unify Einstein's general relativity, which describes the macroscopic world of stars and galaxies, with quantum mechanics, which governs the microscopic realm of atoms and subatomic particles, remains one of the greatest challenges in modern physics. While the other fundamental forces of nature are all described by quantum theories, gravity has so far resisted quantization. This suggests that our current understanding of gravity, as described by general relativity, may be incomplete. Numerous theories have been proposed to bridge this gap, seeking to unify quantum mechanics and general relativity into a single, elegant framework. Quantum mechanics, the branch of physics that describes the behavior of matter at the atomic and subatomic levels, introduces a profound challenge to our classical understanding of space and time. In the quantum realm, particles exist in a state of superposition, meaning they can be in multiple states or locations simultaneously until observed. This probabilistic nature of quantum events challenges our intuitive notions of cause and effect, suggesting that the future is not predetermined but rather a tapestry of possibilities. Furthermore, quantum entanglement, a phenomenon where two particles become linked and share the same fate, regardless of distance, suggests a deeper connection between entities in the universe than previously imagined. Attempts to reconcile quantum mechanics with general relativity have led to intriguing possibilities, such as the holographic principle. This principle suggests that our three-dimensional universe could be a holographic projection of information encoded on a distant two-dimensional surface. The quest to understand the true nature of space and time is far from over. Despite the remarkable progress made in physics over the past century, many mysteries remain. The recent detection of gravitational waves, ripples in the fabric of space-time predicted by Einstein, has opened up a new window into the cosmos, allowing us to hear the universe in a way never before possible. The study of black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape, continues to yield valuable insights into the nature of gravity and the limits of our current understanding. These cosmic behemoths are now recognized as fundamental components of galaxy evolution and provide fertile ground for testing the predictions of general relativity and exploring the potential unification of gravity with quantum mechanics. As we continue to explore the cosmos, we can expect to encounter new challenges and paradoxes, forcing us to reevaluate our place in the universe and the very nature of reality itself.